Right, so we're going to move on to part 2 now of this paper. So we're looking at Gibbs free energy here, and they've given us the equation, which is quite nice. Helps if I don't move the page around, which is slightly disconcerting. So we've got the equation there, and basically they've given us a straight line graph, so they want us to relate this to y equals mx plus c, which is the equation for a straight line graph, because they've asked us about the gradient of the line and the values p and q. So p here is going to be delta H of the reaction, because that is when your temperature is 0. So when the temperature is 0, that expression goes, so delta G equals delta H. The gradient, as you can see from this expression, X is going to be minus delta S, and Q here is when the feasibility of the reaction changes. So obviously the reaction is feasible here, but it's not feasible here because delta G is positive and delta G must be negative. Okay, so why is equilibrium 1 a heterogeneous equilibrium? Well, hopefully you can see you've got the species in different states. You've got 3 things in the solid state and 1 in the gaseous state. So write an expression for Kp. Kp, it's really important that, as you know, and also for Kc, solids aren't included, so you can ignore that, and that. So it just becomes the partial pressure of carbon monoxide to the power of 4. Okay, so part 3 then. Forward reaction is only feasible at high temperatures. Show that it's not feasible at 25 degrees C. Well, first of all, you need to convert temperature into Kelvin. Then you need to pop it into the delta G expression, remembering to convert delta S into kilojoules per Kelvin per mole, which you do by divided by 1,000. Pop it all in, you'll get 467 kilojoules per mole, which delta G is obviously greater than 0, so it is not feasible. Minimum temperature is when delta G is 0, so delta H divided by delta S. You pop these expressions in again remember to divide delta S by 1,000, and you get it to be 962 Kelvin. Right, so for this one we're going to do a Hess cycle, so a nice bit of AS chemistry here. You've got they've given us formation data, so let's pop the elements at the bottom here, and arrows obviously go up. You've got Fe3O4, and so you put that there, and then on that arrow will also be plus the 4 carbon monoxides. This value here is minus 13.5, and then on this arrow you're obviously going to have the 4 carbon dioxides. And when you times that together, that comes to minus 1,574. This arrow and this arrow are going in the same way, so you put those on the same side of the equation, and that equals this value here where the arrow is going the opposite way. Rearrange, remember to divide by 4, and you get minus 110.5 kilojoules per mole. Right, so going on to rates of reaction now. So we got the equation for the decomposition of hydrogen peroxide there, and they've told us how much hydrogen peroxide the student is using, and they want us to find out how much oxygen I'm going to produce. So first of all, you find out the number of moles of hydrogen peroxide, which you do here. The volume of oxygen, it's a 2-to-1 ratio, divide moles by 2, and then times by 24,000, because they've said it's at room temperature and pressure, and you get 690 centimeters cubed. So the thing you need to remember is they have asked you to suggest apparatus, so you use a 1 decimeter cubed gas syringe or measuring cylinder. Right, over the page they've asked to determine another way of doing this experiment to find rate. You could also measure mass loss as well, because you're producing a gas, so you could produce how the mass decreases over time. Then over the side they also ask you to do a few calculations. So they want me to determine the initial rate of reaction, the order of the reaction, and the rate constant. So initial rate of reaction, I've drawn a tangent here, And if you then measure the gradient of the tangent, it hits here at 2.3. It hits here around about 1,300. So to find the gradient, 2.3 divided by 1,300, and it gives you 1.77 times 10 to the minus 3 moles per decimeter cubed per second. You can then rearrange the rate equation. It's first order with respect to hydrogen peroxide, which I'll come on to in a minute. If you do that to find K, you will find K to be 7.70 times 10 to the minus 4 seconds to the minus 1. Okay, and then finally, why is it first order? Well, hopefully you can see that if you put half-lives on here, which I won't do because it will mess up the formatting, it has the same half-life. So remember, half-life is the time taken for, let's have a go, for the reaction to decrease. So going from 1 to 2 to 1, and then 1 to 0.5, you can see that this distance is the same as that distance, and therefore it's got a constant half-life, so it's first order with respect to hydrogen peroxide. Right, okay, so nice equilibrium question now. So explain in terms of Le Chatelier's principle the conditions of pressure and temperature for a maximum yield, and explain why operationally it may be different. Okay, so first of all, let's have a look at pressure. So I have got 4 moles of gas on that side, but only 2 moles of gas on that side. So I want to use a low pressure to drive the equilibrium to the right hand side. Finally, next one is an endothermic reaction. Endothermic reaction therefore means I want to use a high temperature to drive the reaction in the endothermic direction. Why may it be different? Well, because a low pressure will give you a slow rate, and a high temperature will increase the amount of energy that the operator uses. Okay, so part B then, we're now going to do some calculations for Kc. First of all, it wants me to write Kc for that reaction, so don't forget square brackets for Kc, and I've popped it there in part 1. Units, if you hopefully you can see, you're going to have at the bottom, it's going to be 1 over moles per decimeter cubed, and so it's going to be like that. So when you turn it over the other way, it's going to be decimeters cubed moles to the minus 1. Right, now we've got to determine the amount in moles in the equilibrium mixture. So first of all, they've given me the moles of sulfur dioxide and oxygen in the equilibrium mixture, but remember you've got to convert them into concentration first of all, and they've told me the volume of the cylinder or the gas mixture is 400 centimeters cubed. So you find your concentration of SO2 and O2. You then bung that into the Kc expression and rearrange it so that SO3 is on its own. So it becomes Kc times SO2 squared times O2. Put those in the expression there, and you'll get 37.45. You then got to square root that, which gives you 6.12 moles per decimeter cubed, but they want the amount in mole of SO3. So you know your concentration, so you need to now find out how much of that is in 400 centimeters cubed. So in order to do that, you would divide this number by 1,000, 6.12 divided by 1,000 times by 400, and that will give you that number there. Notice they have asked for an appropriate number of significant figures, so it's going to be 3 significant figures because everything else is, well, that's the minimum that they've given you up here. Okay, now we're going to move on to some acids for this question. So we've got a pH meter and it's measured the pH there, so I've got to find my concentration of H plus first of all. So I use this expression to do that, and my concentration of H plus is 3.63 times 10 to the minus 3. Rearrange, well, Ka is going to be then H plus squared over Ha, where Ha is the acid. You put your concentration of H plus there, Ka, they've told you, is here. So you put that in the expression, and the concentration of HA is 0.753. Remembering that number there is this one here. Okay, ethanoic acid added to another weak acid, fluoroethanoic acid. Told you it's Ka. Now notice its Ka is higher than this Ka, so it is a stronger acid, and therefore this acid will put its H plus onto that one there, as I've shown. So this therefore is acid 1, means this is base 1, means this is base 2, and this is acid 2, like so. So those two are related, and those two are related. Okay, so we've now got a nice buffer question. So first of all, they've given us a mass of sodium ethanoate there. So you're going to find the moles of sodium ethanoate, and then finally find your concentration of sodium ethanoate, which you've done here. As I say, whenever they give you a mass, work out moles. So you've got your concentration then you can rearrange your K expression to find your concentration of H plus, which we've done here. Ka, they told you on the previous page. Do you know your concentration of HA? They've told you it up there. You've just worked out your concentration of A minus. And if you do that, you'll find your concentration of H plus to be 3.16 times 10 to the minus 5. Bung that into your pH expression, and that will give you 4.50. So the experimental procedure is correct. When the student prepares a buffer solution, the volume of the solution slightly increases. Will it affect it? No, it won't affect it, because remember, it is only determined by the ratio here. So if you increase the volume, both these values will decrease, but by the same amount, so the pH will stay exactly the same. Right, okay, so they've now want me to draw a lab setup to determine the electrode potential for 1 and 3. So make sure you actually use 1 and 3 and just label it up. Obviously for the iron side, you've got to use a platinum electrode because there isn't a solid metal there. Standard conditions, 1 mole per decimeter cubed and 298 Kelvin. What's going to be the cell potential between 1 and 3? Well, it's going to be the difference between those two. So the difference between 0.77 and also 0.76 is going to be 1.53 volts. The next question is to tell me which is the strongest reducing agent. So the strongest reducing agent is going to be the one that is most easily oxidized. And the one that is most easily oxidized is going to be zinc, because it's the most negative cell potential. So that one wants to go that way and become oxidized, lose electrons. Conversely, they then want me to find out the strongest, let's just have strongest oxidizing agent. The strongest oxidizer is going to be MnO4 minus, because that's the most easily reduced. It's got the most positive E value. Okay, so they now want me to determine the overall reaction for 2 and 4. So if we have a look at 2 and 4, 4 is the most positive, so 4 is going to go that way, and that one's going to go that way. What I've done is I've times the sulfate by 5, so that I end up with 10 electrons here, and the manganate by 2, so I ended up with 10 electrons here. So now we've got to put it together. So let's try doing that. So I'm going to start here. I'm going to have 5H2O plus 5SO3 2 minus, that should be. Let's just get rid of that. That should be a minus. And that's going to, and also I'm going to add 2MnO4 minus plus 16H plus you obviously ignore the electrons, and that's going to go to 2Mn2 plus 8H2O plus 5SO4 2 minus plus 10H plus. Bit of a confusion between my pluses and my arrows there, sorry about that. Okay, so now we need to do a little bit of cancelling. So if we start cancelling, you will hopefully notice that you've got 10H plus on the right hand side and 16 there. So if we get rid of our 10H plus there, we can cancel that to 6H plus there. I've got 5H2O there, so let's get rid of that, and I can cancel that to 3H2O there, and that is the complete equation. Right, so a little bit of transition metal chemistry now. You've really got to know this. It's quite difficult to guess it. I've written the products there. Nice bit of copper chemistry and different ligand substitution reactions. So reaction 1, they asked you what is it? Reaction 1 is ligand substitution, going from there to there. You've obviously replaced the water ligands by chloride ligands. Reaction 2, going from there to there, is going to be a redox reaction. You've started off with copper 2 here, and you've ended up with copper 1 there. Right, so final 6-marker question. Starts off quite, well, it's not too bad actually. Starts off quite nicely. You can get a few marks with an empirical formula, which I've done there. You just take your percentage mass, divide by your RAMs and find the simplest ratio. Perhaps slightly more difficult is finding the relationship between anhydrous complex B and waters. So they've told you from using these figures up here, the value of these two, difference between those two, will tell you the amount of water that is present, and the difference between that one and that one will tell you how much of anhydrous complex B you've got. They've told you the molar mass of B here, so from that you can find the moles of B, moles of water. Simplest ratio is 1 to 2, so you know you've got 2 waters there. Now they've told us that the anhydrous complex B contains cation C, which is nickel, carbon, nitrogen and hydrogen only, and contains 3 molecules of the bidentate ligand D. Well, if you have a look at those atoms, which atom is going to be the donor? It's going to be nitrogen, isn't it? Because he's got the lone pair. Chlorine is not involved in the ligand. They've told you that up here. So if you have a look, you've got 6 nitrogens and 6 carbons. So it looks like you've got a bidentate ligand, so you need to have 2 nitrogens like so. So for every 2 nitrogens you get 2 carbons. So it looks like you've got that going on, and then you're going to have NH2 there. So you've got that as being your ligand. Then in terms of your structure, you've got 3 of those, so you can have optical isomers, which I will draw on the next page. So you're going to have your nickel in the middle, and then we're going to just do dash, 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 wedge, wedge, duh, duh. I then put your nitrogens on like so. You can then put I put your carbon on like so. You can put your H's on as well, like so. H2, 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 and H2. And then you want this is obviously going to be 2 plus, like so. Because your nickel is 2 plus, and you haven't got your ligands and neutrals. Then you're going to have your mirror image of that, so let's do that. Just do exactly the same structure in terms of your bonds. Put your nitrogens on like so, and then your mirror image is going to be like so, and then you can put your H's on as you've done before. and that is also going to be 2 plus. Your counter ion is going to be 2 times Cl minus. 2 times Cl minus. You can look at that because you've got a total of 2 chlorides in your empirical formula. And I think that pretty much answers everything that they wanted for that one. So it's not too bad. As I said, if you don't get to the final complex, then at least have a bash at the empirical formula, and you know, having a bash at doing the ligand pictures as well.